I know.
Okay, hi, I'm not Marcella, but I'm Larissa. Marcy's running a little bit late, so I'm gonna do the introduction. So this is a collaboration between Altair Engineering and SACNAS, the Society for the Advancement of Chicanos, Hispanics, and Native Americans in Science at UH, the University of Houston chapter. And this is a continuation of our collaboration series, kind of getting people introduced to machine learning and some of the tools that Altair Engineering has developed and is allowing us to learn. So thank you guys so much for being with us, and thank you guys so much for helping us with this collaboration. And it's nice to see you again, Sebastian and Darius, and welcome to Martin. I think I haven't seen you before around here. Thank you guys so much for being with us, and thank you to the participants. We have a raffle that we're going to do, and we have a form. I'll put the link to the form in the chat, and you guys will be able to go and put your email in for the chance to win one gift card.
All right, Martin, I think you can, as long as you can share your screen, you can start your presentation.
I need to be made presenter so that I can start to share. Otherwise, I may just start to introduce myself while I'm if somebody could make me presenter, that would be awesome. So my talk today is called Data HPC Simulation and the Universe, because I thought it's good to catch all things. And it's a bit about my journey and how I interacted with Altair software for the past, 13 years without really being, without knowing that much about it. Just enable screen sharing. Okay, then we can do it like this. And now you should see my screen, and if not, you can tell me. And so what will we talk about? Anybody knows what this is? Sebastian, I'm not sure if I can put you on the spot here as well to make it a bit more interactive.
Is that the Crab Nebula?
Okay, that was good. That was good. Are you a hobby astronomer?
No, but my thesis is on supernova detection through neutrinos.
Okay. So the Crab Nebula is a supernova remnant. It's kind of interesting if you look at it, how we discovered it, or who discovered it first. Basically, it's a supernova which exploded in around about 1054, and Chinese astronomers saw it. So it's one of the first cosmic events where astronomers on Earth could see it. And later then in the 1800s, we did a ton of analysis on that, because 800 years ago, or that's when we saw it, it's of course further away and light travels and everything. We still study it because it's a very interesting phenomena in space. And we'll come back to that a bit and try to understand how we learn about the universe. So a bit about myself, you probably heard I'm German. I studied physics at TU Dortmund University. That's somewhere where the red dot is here, North Rhine-Westphalia. And I started my science career, so to say, with simulation, which is one of the things Altair is doing. I simulated charged leptons traveling through ice, and we will learn why this is important. And then I did my PhD in physics, analyzing neutrinos from outer space, very similar to what Sebastian will talk about. And then after my PhD, you sit there and ask yourself, what do you do as a physicist? No real business is interested in neutrinos, so what do you do? And there are, broadly speaking, two big avenues you go. One is consulting, One is data science, and then there's a combination of it doing consultancy for data science. So I joined a company called RapidMiner in 2014 as a data scientist, and very quickly moved a bit outside of data science towards something which is called pre-sales engineering, which basically means you want to sell software. And when you want to sell software, you need a salesperson for it, but also a person who knows the technology, but is part of the sales process. And that's what I did for a few years, like with a team of people trying to sell the software, which we'll talk about later. About 16 months ago, RapidMiner was acquired by Altair Engineering, and now I'm part of Altair and still do data science as part of a global team. So we want to go into what do we know about space? And then the first big question, which should be at hand for everybody here, is how do we learn something about the universe? What's the universe doing? So if you think about it, how do we know something about the universe? The first thing you may do is you look up. And then you see the Milky Way, and you may use telescopes. And then there were like famous people like Galilei or Brahe or Copernicus and so on, who analyzed what happens on the firmament by just looking into that, sometimes with a telescope or without. And we do this for thousands of years. And this is how we discover things in our own planetary system, or Andromeda, or for the sake of it, also the Crab Nebula, which is part of the Messier catalog. But then, of course, at some point, you looked around and asked yourself, how do I learn more about the universe? I want to understand how the universe works. What do I do? So what you do is, well, you can look into the infrared and build a detector which detects infrared. And that way you learn more things about the universe, because the universe looks differently in the infrared sector. All right, we can go to even less energy. And we can look at something, this is also, Sebastian, you will know it, a very famous picture, because that is the cosmic microwave background, which is radiation, which is in the universe, which stems from the Big Bang. There are studies on this, and it's a fascinating topic, how you learn how the Big Bang works, or something right afterward works, because that's when this cosmic microwave background was generated. And that is essentially also light, but in a different energy range. You can do the whole thing on the other side of the spectrum, and you can look at extreme energies, energies which are in the energy level of what happens at CERN and at Tevatron, and look at gamma rays. And then you can look at Earth. And by the way, there's our old friend, the Crab Nebula, again, which is a source for extreme high energy radiation hitting us, which is interesting to see. How does the universe create such high energy waves which are traveling through everything? And, you know, for basically centuries, that is what astronomy was. You know, you look at the spectrum, and you started with, you know, I look up and look how the Milky Way looks like and everything. I looked at ultraviolet, or I first go into increasing wavelength and also to higher, and that's how I learn about the universe. And most of what we know about the universe comes from this, from analyzing light particles, photons, in different energy regimes. And that's how we made a picture of the universe. Okay, cool. We learned something. But what's the problem here? Why do we now talk about other things? Well, light has, I think, at least two big problems. Light cannot travel through walls, or it gets absorbed by intergalactic or galactic dust clouds. So you cannot look behind something with light. That's one problem. Also, when you think about where this extreme radiation is generated, the most extreme one may not even be able to get out of that because it's blocked by dust or by the source itself. Problem number one. Problem number two is light is always connected to electrodynamic or quantum electrodynamic. So by looking at light, you will only see processes which are connected to those, where light is, or photons, better to say, because we're talking about different wavelengths, but it's light essentially, just in different energy ranges. You only see processes where photons are generated as a byproduct. You're blind for anything else. So we may say for a long while, we've only seen a part of the universe, the part which is accessible by light. And now you may ask yourself, oh, what else can we do? If we don't look at light, at what else can we have a look? And then you go to your physicist of choice and ask what kind of particles are around there. And then they come up with something like that, which is the standard model for elementary particles, which are basically all fundamental particles we know about. And let's first maybe talk about those ones here, the quarks. You may have heard about it. Basically, all matter which we know or which we interact with in our daily life consists of up quarks, down quarks, and electrons, because up and down create protons and neutrons, plus an electron. Now I can go to my chemist of choice and talk about the period system and how you can make nitrogen out of that, or oxygen, or sulfur, or whatever you want to. So you may ask yourself, okay, are those things hitting us? Are protons hitting us? So hydrogen, oxygen, and all those things? And the answer is we checked. And yes, they do. So this is a spectrum of particles hitting Earth for different energy ranges. And with like tons of experiments, we spent tons of time measuring this, this spectrum. And you see down here, this is the power of our best accelerator on Earth, the Large Hadron Collider in CERN in Geneva. And this is the one in Chicago, I think, the Tevatron. And you see, this is a logarithmic scale. So yeah, there's a factor of 100 or more coming in here. So every day there are particles, and we're talking about protons, helium, and everything hitting Earth, which are way, way, way more powerful or energetic than what we humans can create. So there are forces in the universe which create particle of such energy humans cannot generate at all. That's why I'm not sure if you heard when they started CERN, like when they started the LHC at CERN, people are talking about, oh, black holes will consume Earth, and because of this, everything will go down. And most physicists were like, yeah, but like every day, more energetic particles hit Earth, and Earth didn't disappear, so maybe it's not that worrying. So what's the problem with that? So we've spent significant amount of money and time to generate this spectrum where we see, and there are a lot of theories, and you can do theoretical physics, that this one here is generated in our galaxy, while these one here are actually created in another galaxy. You know, we're talking about very violent phenomena where neutron stars collide, or black holes with a circulation disk around them, like the most crazy thing you see in maybe Star Trek or something. Yeah, maybe not that good of an example. What's the problem with that? Well, most particles either have a charge, like a proton, or basically we're talking here about helium ions and not about helium itself. So they get deflected by electromagnetic fields. And there are electromagnetic fields in the universe. So you basically have a particle which is distorted and it hits Earth, but you have no chance figuring out where it came from. So it's nice to see this spectrum, but you cannot point to this is the source of it, because electromagnetic fields are distorting the particle. So we know that there's stuff going on. We know that it is interesting. We want to learn more about it, more than just with light. But those protons and helium particles and so on are not the answer, because we cannot point to the source. So what we want to do is called multi-messenger astronomy, where we want to use different particles to learn about the universe. And then, you know, you walk back to your physicist of choice and ask, hey, physicist of choice, what else can I use? I've tried protons, I've tried helium. By the way, most of the more advanced particles, like muons or so, also decay. Like even neutrons decay when they're unbounded. So your physicist of choice will tell you, listen, most particles either have a charge, so you can measure them, but you don't know where they're coming from, or they decay. So you may not see them because they don't have the time to reach Earth. But there are two very interesting particles around there. By the way, there's this funny website, particlezoo.net, where you can buy yourself like plush particles. And I find that hilarious. But funny. And those two are called graviton, or gravitational waves, better to say, and neutrinos. And I don't want to go too deeply into gravitational waves, because I'm by far not an expert on that. But you probably heard that there were a Nobel Prize on detecting gravitational waves. And, you know, there's another rabbit hole we can go into. But what I want to talk about is to use neutrinos as a messenger from outer space, and what this has to do with Altair, or Altair's technology, better to say. So what are neutrinos? So neutrinos are nearly massless. That does not mean, so we know that at least 2 of them have a mass. There, by the way, at least we know about 3. There may be a 4th one, which is an interesting question. So they are nearly massless, which, by the way, also means they are not distorted by gravitational fields, so by the pull of a galaxy or something, which is useful. So they travel in a straight line because they also don't have an electric charge. So they get not distorted by electromagnetic fields. So basically, from the source, they are going straight up. And by this property of not doing anything with the electric charge, they also have one tiny problem, which means they don't do anything. Neutrinos can fly through the whole Earth with a low probability of doing something with the matter of Earth. If they do something, then there's for example, a muon neutrino. As I said, there are 3 of them. We'll focus on the muon neutrino. It flies, and then by random chance, very rarely, it interacts with a proton, and you get a neutron, which is not interesting, but also a muon. And the muon, or it's actually an anti-muon here, is then traveling through the matter. So what we want to detect is that muon, which comes from the muon neutrino. And there's something, I'm not sure if you ever saw that, the so-called Cherenkov effect, which means when a muon is traveling through a matter and it's faster than the speed of light in this matter, then it's emitting blue light. And that's also what you can see in those test reactors. They sometimes, if you see pictures, are glowing in blue. And that's this Cherenkov effect, that if you have a high energy particle going through matter and it's faster than the speed of light in this medium, which is always smaller than the speed of light in vacuum, then they emit this light. And that's the trick we want to use. We want to detect muons which are induced by neutrinos, which come from outer space with this Cherenkov radiation. So I've been part of that hunt as part of the IceCube collaboration. The IceCube collaboration is a collaboration with dozens or even more, it's way more, institutions, most of them either in Europe or in the United States, but you see there's Canada, there's Japan, there's Australia, collaborating to build a detector. So what kind of detector do you want to build? So you need something which is big, because the bigger it is, the more likely it is that you actually detect something. Because remember, neutrinos rarely do anything. So it needs to be very, very big. On the other side, it should be transparent, because we want to detect the light, the blue light coming from the neutrino, the muon going through the matter. So we need a big thing in a transparent environment, and this naturally goes down to 2 things which you can do. You either build something in seawater. There's something in the Mediterranean called Antares, or you build it in ice. So the detector I was working on, the IceCube detector, is a cube of 1 × 1 × 1 kilometer size of instrumented volume, directly below the geographic South Pole, where you see the size is gigantic. And the effective size is even bigger, because those high energy muons, which come from the neutrinos, which come from outer space, can travel for a few kilometers through the ice until they are gone. And that's why we look at muons, because electrons have only a few hundred meters, and the third one, the tauons, actually decay so quickly that also in a few hundred meters, they are created, they travel for a few hundred meters, and then they decay again. So the nice thing about the muon is that you actually can see them for a few kilometers, and that's why the effective size of this detector is even bigger than this 1 × 1 × 1 kilometer. And down there, so we drilled holes on the South Pole, and there are so these little spheres called DOMs, digital optical modules, which are in the end something like a light detector, detecting the blue light. And then you can take data, and I got a little video of a neutrino coming in, or better to say, that's the reconstruction, and then it travels through it, and then you see how the different DOMs are activated, and of course, the bigger the bubble, the more charge it got, and this is what you detect in the detector. All right, looks easy, right? I need to speed up a bit, I think. Here's the problem. If a proton hits Earth, it does stuff, and that's the cosmic radiation. And while it does stuff, it creates muons and muon neutrinos. That's, by the way, part of the radiation. When you fly transatlantic, you're at 10,000 meters or something, you're right in this shower, and that's the radiation you get. But part of what's generated is muons and muon neutrinos. So it happens that you're in the following situation. Down here is ice cube. And there's this source neutrino we want to see, which generates a muon here and travels through the detector. Also, there's a proton hitting the atmosphere, creating a neutrino. The neutrino is going through Earth as well, interacting, also creating a muon, traveling through it. And from the other side, you have the atmospheric muons. See, here you create muons and muon neutrinos, which are then directly going in the detector without a neutrino. That's, by the way, why it's 1,000 meters deep below the ice, so that you get a bit of cover from it, that particles actually stopped. And we are only interested in those ones here. And I usually compare this to you're standing in the rain, and from above, there's rain coming down. And there's one rain bubble which goes up. And you search for this drop, the one drop which goes up and not down, because the one which goes down are the muons which are generated in the whole own atmosphere. And the ratio between the signal and the background is 1 to 1,000,000. So what do you do? Well, I can say I only look through Earth. So I only look what comes from the Earth core. And then maybe also I say I only take those where I have a good risk construction quality. And that way I figure out, or I only see, well, at least non-muons. I see neutrinos, because everything else can't go through Earth. That's already good. But you see, this goes into the direction already of a tree, a decision tree. And if you're familiar with machine learning, you can ask yourself, can't I do this better? And can't I use an artificial intelligence to distinguish between the thing I search for and the thing which is around there? And the answer is, yeah, that's the plan. But what you need to do first is you need to create yourself examples for signal and examples for a background. You don't have that. So this is, remember, the talk was called Data Simulation, HPC, and the Universe. Let's go into simulation, because that's what's been done. You simulate everything. You simulate the protons which hit Earth. You simulate this whole shower of particle physics happening here. You simulate the propagation of the neutrino through Earth, that it happens by random chance that it's doing something. You simulate how this muon travels through matter. You simulate how the light is generated, and you simulate the electronics of the whole detector with all the noise and everything. And that way you can generate yourselves neutrinos and muons in a virtual world. And remember, when I start my talk of what did Martin do, I said I did simulation. And what I did is I wrote code which basically creates or lets those muons or electrons propagate through matter. And while they do this, they also interact with the matter. Create an electron here, an electron there, inelastic scattering here, and so on. And that code is what I wrote in my master's thesis. Was more computer science maybe than physics, but that was my first interaction with simulation. The issue is, or what means issue, you need to create a lot. You need to create so much or so many particles that you need a cluster, a compute cluster. And the fun fact is that what I've used in my thesis was a PBS cluster. And PBS is one of the software packages Altair sells as a product. So I was using Altair kind of software. I'm not sure if PBS was actually part of Altair back then already in my thesis. So you do the whole simulation and simulate and simulate and simulate so that you can get a simulated version here of it and the whole signal. And here I know whether it's a muon or a neutrino, or a muon which is neutrino induced, or an atmospheric muon. And I can describe this whole thing with attributes. I can collect the total charge this particle left in the detector. I can collect the maximum charge. I can collect the center of gravity of the whole line here of all data points. And there are tons and tons of additional reconstructions going on, like the angle. And then if you do a fit through these data points, you get a goodness of fit. If you got track length through the detector, how far is it? There are concepts like it's a corner clipper, so a muon which only passed through the corner of a detector. There are values or there are analysis going on which estimate the energy the muon had when traveling through the detector. And for all of you who got in touch with machine learning, well, you got a machine learning problem here. You have rows of data where you know the whether it was a neutrino or a muon initially, and you got tons of columns describing this event in the detector. So what you can do is you can train a machine learning algorithm, or how I love to call it, a pattern recognition algorithm, which separates between the two parts. There are some tricks going on, like what you throw in, what you don't throw in. When I did my thesis, remember, this is a few years ago. We've done this on these reconstructed values. My supervisor actually published a paper recently where they use deep learning, which goes rather on the original values than on the reconstructed values. Because what you have here is a movie. You got a small movie sequence, which you want to analyze, and you can use deep learning for that. And you get better using these systems. But what I've used was based on those columnar description. And I used the software for this called RapidMiner, and I joined this company right afterwards. And I've used this version of it, which really, I've spent a lot of time in that. That is RapidMiner 5. We are now at RapidMiner 10. So that is RapidMiner from 8 years ago. And the advantage of this software, if you download the new one, everything looks nicer. But I want to have this flashback here, is that you get some data set in, and then you can add block after block after block after block and build yourself an analysis like that. And I've spent tons of time in this software to generate a good separation between muons and neutrino-induced muons. And the result of that was that you see, you could like tune the algorithm a bit on how selective it should be, but then with this algorithm, you find like 60% of all, around about 60% of all the neutrinos which were still in the data set. There's some additional cuts in the beginning you can still find, and that is of course way, way better than what you can do manually. When I did my thesis, there were, I'm not sure if there are still people around who do this manually, who do this, what I showed earlier with this tree structure, saying, okay, I select only events which come through the Earth and have a good reconstruction quality and have a total charge which is high enough and at least have 200 meters of track in my detector. And, this human way of thinking of selection, you can just show that using machine learning for that is way stronger. And that way we created ourselves a sample of, I think, 5,000 events a year, which are for sure not muons, not atmospheric muons, but neutrinos. There's a slide missing. Here's a problem with that. Let me go back to this one here. Now, what this whole effort did is that you got rid of this. You still have this and this in your data set, but you're only interested in the source neutrinos, the one coming from outer space, because remember, we want to learn stuff about the universe. And luckily, there is a difference between those and these, which is the energy spectrum. Basically, if you think about it, atmospheric neutrinos drop off at some point in energy, while there should still be more source neutrinos. So the higher energetic you go, the more there should be source neutrinos compared to atmospheric neutrinos. Now, the problem is what we got here. I mean, we only have those patterns in our data set. And if you look at reconstructed energy compared to the real energy, and this is again in Monte Carlo land. So in the simulation world, you know what you put into and you know what you get out of it. And if you then compared it, you see that, well, there is a correlation here, but if the true value is like 3, so 10 to the power of 3 giga-electron volt, then in reality, it can be between 2.4 and 3.5. So it's not that good. And that's a problem. So we wrote some software to say, okay, I'm not interested in the energy of a single particle, but what I'm interested in is the spectrum of particles. I lose information about a single one, but therefore I get an estimate for the spectrum. And this is basically the result. What you see here is, again, similar to what we saw earlier, the protons, basically the neutrinos hitting Earth for different energies. And this green curve is what you expect, which comes from our own atmosphere, the protons hitting it. So the not so interesting one. And then there's a second component to it, if you look into theory, of those atmospheric ones, which are not 100% understood, and this is the purple one. But you clearly see that the measurements of the IceCube detector says, well, there's significantly more high energy neutrinos observed than what we expect from theory, if you sum up the two lines. So what I've done is I found atmospheric astrophysical neutrinos with a